this one will be a presentation that will give you an idea of the activity that have been performed in these 2 years as partner, okay, in this project. And without giving also here an introduction from the general point of view of the project, I just point out that we, let's say, substitute the Veneto region in this project in 2021, and then we enter as a new project partner, let's say, for this for the activities. So going directly to our activities, our department acts on this following side. So first of all, for the seismic risk, the objective was to investigate the impact of deterioration of existing structures on the overall seismic risk, with special attention to existing road bridges. While as regarding, let's say, the activity are training activities, also in this case for the seismic risk, there was a promotion and funding of training courses and practical exercises for firefighters, with the aim to strengthen their skills and capabilities in the field of technical triage, and of a technical seminar for IDES technicians and local government officials for the coordination of this impact assessment, damage surveys, and post-event, okay, seismic event for the accessibility in buildings. And as regards the other activity from the other side, also we worked also in the earthquake fire interaction, investigating how can we have the fire ignition risk caused by an earthquake on different type of structures, so pre-stressed concrete, steel, masonry, and wood structures. So starting from the seismic risk, first of all, and going to see a little bit more regarding the deterioration, the role of deterioration on existing structures, we can say that as regards the visual inspection, these are essential to obtain a photograph and, let's say, a descriptions that can be objective of a given moment, for a given moment of the actual condition of an infrastructures. This type of inspection should not be, let's say, should not use sophisticated instrumentation, and as a rule also should be not so, let's say, let's say that need a lot of temporal resources. So the suggested basic instrumentation includes simple measuring instruments to perform the geometric relief of the structures, photographic instruments for a performance of adequate of the execution of photographic reliefs, and also other instruments that can be useful for the relief of the main characteristic of our structures. So during the activities that have been carried out in this project, also drones were used to capture images during this visual inspection. And in particular, the use of these drones allows to reach areas, for in this case for bridges, that could be, let's say, inaccurate without the use of by bridge or platforms. And using this type of drones, let's say that the inspection using these equipments must be carried out by trained personnel. In particular, here we can see some, let's say, characteristic and equipment that are for these drones, so our instrumentation. So the research team for this part has carried out, let's say, 60 seismic risk assessment in the last year. In particular, here we can see a series of photos for different type of bridges. And this infrastructure that have been evaluated were divided by material, static scheme, age, and the level of defectivity that will be evaluated in relation to the seismic risk. So based on this survey, the most common level of defectivity is medium, and this is going to reflect the fact that almost half of this infrastructure were built after 1980. And most of the defect found concern the support devices. So this is very important if we think about it then to an earthquake. And this parameter, the defectivity, will affect the level of seismic vulnerability. So if we move here, this deterioration is going to impact directly the evaluation of this vulnerability, and the deterioration scenario that will be have been collected during the surveys during this project showed a strong correlation between the seismic defect levels and the related seismic vulnerability evaluation. And if we go to see the results, we have that almost half of the cases are in a medium class of vulnerability, the 25% in a medium high class, and 10% in a high class of vulnerability. Okay, so moving to the second part of the activity regarding the seismic risk, as I said before, also in this project, we promoted and funded training courses for firefighters. In particular, we promoted the training course Technical Triage for Assessment and Treatment of Structural Criticality from Seismic Events. This was a course that, let's say, was built up in 36 hours and was involving 60 firefighters from Veneto region. And during this course, they learned, let's say, procedures and tools that could be useful to carry out surveys on the practicability of roads for rescue operation and assistance to affected population, the usability of buildings, identification of areas that can be interdicted, and any other information that can be useful to local authorities, also for the implementation of the urgent civil protection intervention. At the end of May 2023, the firefighters had also the opportunity to consolidate their theoretical knowledge by participating to a technical exercise in Berzone. This Berzone is in Provincia di Udine, at the CERM Academy, that is the Seismic Emergency Response Management International Training School. That is an area that was affected by the 1976 earthquake, where partially collapsed and heavily damaged buildings were preserved. So in this case, these firefighters, let's say, work on quick triage operation, and they were subdivided in 10 teams. After this technical operation, at the end of this, there was a final debriefing activity that was coordinated by Professor Stefano Grimaz. Sorry. Okay. Okay, perfect. It was coordinated by Professor Stefano Grimaz, that is a scientific coordinator of this academy. After having contributed to the strengthening of the skill and capabilities of Veneto region, let's I think that I have to, there was a request, no. But I don't see it. Okay, I will proceed. After having contributed to the how can I say, to the skill, to, let's say, enforce the skill and the capabilities of the Veneto region fire brigades in the field of technical triage, our department expanding the target audience. So, considering the importance of expeditious surveys for the adoption of appropriate measure in the post-seismic phase by the competent territorial bodies, a seminar that is called Operational Indication for the Coordination of the Impact Assessment and Damage Survey Activities and Post-Seismic Usability of Buildings was organized at the end of June at our department. This one was, let's say, addressed to AEDES qualified technician, local government official, and civil protection, with the aim to obtain at the end, let's say, a coordination in the activities between the fire brigades and the civil protection and these technicians that are involved after a seismic events. Okay, so moving to the last part of our activities. As I said before, there was also an investigation of the earthquake-fire interaction in different types of structures. So pre-stressed concrete structures, steel structures, with structure and masonry structures. Here, I just briefly, let's say, pointed out the objectives. So first of all, there was the objective of a production of a document that was framing the existing intervention system at regional and national levels in the field of emergency services, of seismic risk and earthquake fire risk. And in this case, highlighting critical points, deficiencies, and formulating recommendations. The second objective was the contribution in drafting guidelines for a uniform Italia-Croatia cross-border emergency intervention system. And the last two objectives were the production of a document that was describing the theoretical and computational approach for the study of this interaction. And finally, a significant case study was inserted in the document for each type of structure. So let's go directly, because I have no time, to the last two objectives. So let's go directly in the, let's say, technical part. Here, I just, let's say, put together the standards that found application in this work. In particular, here we have the DM of 2018, that it being understood that with regard to exceptional actions such as fire, the same refers to the application of the Eurocode, as far as it involves the odd behavior of the different structural types. And as can be seen here in this slide from the chart above, we have that the standard provides for two distinct load combinations, one seismic and one exceptional. Therefore, there is no concurrence of the two actions. Similarly, Eurocode 1 points out that there is no need to consider the simultaneous occurrence of other exceptional actions. So, the work done here in the fire spill project was, let's say, a numerical work that was done considering different type of structure, and the numerical model that we will see here were done in Abacus. So in this case, in the particular case here presented, we will start from the first structure that is made of steel. We have that the application of action was considered as a sequential application. So first of all, we have the vertical load, then we assume here horizontal action for seismic nature, and then at the end, the exceptional action. So we, let's say, conducted an entire analysis from the beginning till the end, considering this sequence. So in this slide here, we just put, okay, let me, okay. So as regards here, we can see that this application of the sequence of application of action is shown on the right. So we can see here particularly the spectrum and then the fire load that was using here the ISO 834 curve, while on the left, yes, in this case, we have the structure and in particular the substructure that was investigated on the bottom. In the central part, we have the characteristic curves of our materials, the steel material used for the structure and then for the bolts. And also we have here the specific heat and thermal conductivity of steel. Obviously, we can see here that everything was considering with the variation, considering the seismic event and also the fire event after this. Great, so special attention in this first analysis was given to the connection, applying, as mentioned above, the elastic spectrum and then the isofire curve. And the results that are here reported concern the evolution of the stresses and strains in the bolts and plates that are part of the connection. As it's possible to see here, we can see that the weak point of the structure is represented by the connection, which is, in this present case, results to be unprotected. So in these slides, we illustrate, let's say, the mechanism that we can have in the connection. In the first part here, the first columns show the global deformation of the substructure in terms of stresses, while the second column presents the deformation of the connection and the mechanism. And finally, and in the third column, we can see here the, let's say, the stresses also here for the plates and also in the bolts, and also a force displacement graph. Okay. One thing that I forgot to mention before is that if we look here in the figure on the left, this representation here, so the deformation here of the substructure was related to the vertical load and after the seismic load. While in this figure here, we went to see, let's say, the results of the stresses at the end of the analysis. So we have the fire curve applied after the seismic events. Also here in this slide, we deal with the mechanism of the connection. And in particular here, in this actual case, in the center, we concentrate the attention to the central node between the beam and column. We have, so in the left, the results in terms of stresses, temperature, and displacements after the fire, so at the end of the analysis, while in the other case, where we have the deformation at the connection and the mechanism. Okay, so the second structure that was investigated was a timber frame building with steel connection at both base and top. And with regard to the structure, the properties of the material are here provided. So also here we have the characteristic curves of the material and also the variation of the thermal properties with temperature for steel and laminated wood. While on the right, we have the same action that we have assumed before. So we have the same horizontal spectrum here for the seismic event, and then the application of the isofire curve. So if we look at, yes, perfect. Okay. So if we look at this this figure here, we can see also here on the left a representation of the stresses that we can have in our figure. And as regards the other figure here, we pointed out the stresses that we have in the connection, and so all the mechanism that we can have in the connection after the seismic events. While in this second figure here, for the same wood structure, we have considered here let's say the stresses at the end. So what I didn't point out before, and I would like to point out here, but also for the previous example, is that in the case of this connection, is here that we have a very, let's say, rise of our stresses when we move from the seismic event and we proceed to the fire event. So we have to consider that passing from one event and adding the second one, we will have almost 50% of stresses, an increment of stresses that we have at the end in the connection. So it's important to understand better these points here in the structures. Okay. At the end, sorry, this is not the last, but we have then just a last slide on the wood structure. We have before the pre-stressed concrete structure here. So in this case, we consider a concrete structural element that was forming part of the roof of an industrial building. So first of all, what we did here, we analyzed, all the analyses were done in Abacus. Also here we analyzed, first of all, 1 meter element of this rooftop, of this part of the roof of the building. And in this case, we consider this 1 meter part to calibrate the thermomechanical behavior of our material. So here is reported the geometry. As before, we reported here the action that were applied in the same manner with the same sequence. And at the end here, we can see some results with reference to the previous slides. So we have the results of the thermomechanical analysis related to the 1 meter long tile section, the stress contour, and the stress contour, let's say, for the different steps. So first of all, here we see the stress for the pre-stress definition. So, and we can see here that the highest value that we can have here for the stresses is related to the wires inside that were pre-stressed. Then we have the application of the vertical load as step 2. And here we have, let's say, representation of the stresses for the entire structure and then for the strands and the reinforcement. While in these slides, let's say in the central part here, we are going to see the stress level in the structure with reference to the seismic load and the temperature load application. In what is seen here on the right is referred to the previous cases. So we have here, we can see here that this value of 7 megapascal, that is the maximum here that we have, it is related to the concrete beam for the pre-stress condition, while the second one here for the reinforcement and the concrete beam is related to the vertical load application. Okay. Okay, perfect. So, well, so with regard to the last structure that was studied here, that was this masonry structure, what I want to point out that this is not an analysis that is completed because they were still running the last part, let's say. So at the moment for this earthquake fire interaction, there was also a first earthquake study. But specifically here in this case, so was considered the vertical load and then the application of an horizontal load. In this case here, what was done was an explicit representation of the bricks and also the cement paste that is between the bricks. So we didn't homogenize the situation, but were represented specifically here all the materials. So we have vertical and horizontal here, paste between our brick, the mortar between our bricks in this case. And also here, as done before, for the material behavior here, we consider, we used here in Abacus, before was used the concrete damage plasticity, obviously adapted to the specific case, in order to take care also of this degradation related to the seismic event and also of the fire events. And also here the nonlinearity was given also here to the materials. So here there are just the first two studies that needs to be just completed. for a first study and representation here of the displacement related to the application of the vertical load and then the application of the seismic load with the maintenance of the vertical load. So I am done, and so thanks for your attention.